All right, this is Gold Team Energy Subsector Basics, Hydro and Geothermal. I'm Jake Bravender, and my teammate is Marcus Harverland. He'll be narrating the hydro portion. So I'll go ahead and just jump into geothermal here. Quick overview. So geothermal is just generally speaking heat generated within the Earth. It's a slow decay of radioactive particles from the Earth's core, and it happens in all rocks, and it produces the geothermal energy. So geothermal reservoirs are naturally occurring areas of hydrothermal resources, and these reservoirs are deep underground. And it can be challenging to detect them. It takes pretty advanced technology to find them. There's a lot of exploratory drilling associated with ensuring that the geothermal resources is usable. Geothermal energy finds its way to the Earth's surface in three ways: either through volcanoes and fumaroles, which are just holes in the Earth where volcanic gases are released, hot springs, and geysers. Most of these geothermal resources are near the boundaries of the Earth's tectonic plates. And some applications for the geothermal energy uses the Earth's constant temperature near the surface, while others require drilling, pretty deep into Earth's crust in order to harness that energy. There's three main types of geothermal energy systems. The first is direct use and district heating systems. One district heating system is just a larger scale of the direct use system. Geothermal power plants, as well as geothermal heat pumps. So the geography. Most active geothermal resources are found along major tectonic plate boundaries, where most volcanoes are located. And one of the most active geothermal areas in the world is the Ring of Fire, which encircles the Pacific Ocean, which can be seen in the image down on the bottom right. On the bottom left, you can see the geothermal resources of the United States in a density map, as well as temperature. Well, I shouldn't say density map, but more of a temperature map of the energy produced, and it's largely centralized on the western part of the United States. So direct use and district heating systems. So this is your direct use and district heating systems use the hot water from the spring or reservoir located near the surface of the Earth. And this is what you would see like hot springs and whatnot. Ancient Roman, a lot of ancient cultures really used these for bathing, cooking, and heating. Today, a lot of folks use hot springs for bathing, and they think there's some health benefits to the mineral-rich waters. Practical applications for this system would be it's used to directly heat individual buildings or as part of a system to heat multiple buildings. That would be called a district system. Hot water near the Earth's surface is piped into buildings for heat, and a district system provides heat for most of the buildings in Reykjavik, Iceland. Industrial applications for this can include food dehydration, gold mining, and milk pasteurization. So if you reference the image on the top there, just a rough graphical representation of what a geothermal district heating system would be like. So you can see the water pulled from the reservoir up to a heat exchanger, and it's pumped, and it's heating, the working fluid and pushing it to all the facilities to heat the facilities. Below, you can see the Capitol Mall geothermal district heating system of Boise, Idaho, a practical application of this technology. So geothermal heat pumps. So these heat pumps utilize the Earth's constant temperature for heating and cooling. This is because the Earth's temperature has a constant the Earth's crust, about 10 feet below ground are constantly between 50 and 60 degrees Fahrenheit. So that means it's warmer in the winter and cooler in the summer. So you can utilize this to exchange energy to cool water in the summer and heat water in the wintertime. And the application for this is for heating and cooling facilities and HVAC supplement. So according to the EPA, the geothermal heat pumps are the most energy efficient and environmentally clean and cost-effective systems for heating and cooling buildings. And this is scalable to all sizes, so you can use it at homes, office spaces, schools, hospitals. You can use it. Can use a geothermal heat pump system. The office where I work at, we have 60,000 square foot facility that utilizes a horizontal geothermal heat pump. It's not it works pretty well. We're looking at upgrading the system and incorporating some other facilities into that to reduce our energy as an energy conservation measure project. You can look at the top image there. You can see the summertime there. The heat pump is pulling heat out of the water as it flows from the facility, and cooler water is being pumped back in to assist with the HVAC system. In the winter, it's the opposite. You're pushing heat back into the water, pushing energy into the water for that BTU exchange, and it's assisting heating the facility. And looking below, there's about 4 different applications for the ground source heat pump. You got a vertical one, a grounded loop connector, horizontal, and you can also use, you know, a pond as well. We have the horizontal one at my facility currently, and we're looking at putting a vertical system in. So for the geothermal power plants, we have 3 basic types. We have your dry steam plant, a flash steam plant, and the binary cycle power plants. A dry steam plant uses steam directly from a reservoir to turn generator turbines. This was the first system developed, and it was the first one was ever built back in Tuscany, Italy in 1904, where you had like natural steam geyser coming up, and they were able to harness that energy. Flash steam plants take high pressure water from deep inside the earth, and it is converted to steam, and then that steam is then turns the turbine, and then the steam condenses and turns back into water, and it's injected back into the ground in order to use that water again. This is the most common type of geothermal power plant. You get your binary cycle power plant, transfer of heat from geothermal hot water to another liquid, and this causes the second liquid to turn to steam, and it's used to drive that turbine. Similar to like a district heating system if it's using a working fluid. Look here at the images. It's just a rough, simplified diagram of how the systems work. In order that discuss, dry steam power plant, pulling the steam straight from the ground, turning the turbine. Demonstrate the flash steam plant there, as well as the binary cycle plant. So the market overview for this. The geothermal energy market is currently at $55 billion as of 2021, and they're expecting it to grow to about $83 billion by 2028. So almost a 6% combined annual growth rate for that market over the 7-year period. When considering constructing a geothermal plant, it's heavily weighted. Costs are heavily weighted early on in the development over the development plan. Versus on the operations and maintenance side. It's pretty low maintenance when it comes to maintaining a geothermal power plant. Well drilling and pipeline construction are the first and foremost as far as the construction goes, and then resource analysis of the drilling information is used for the design of the actual plant. How much energy are they able to pull? So what kind of power generation are they going to get from that? Typically you can see about $2,500 per kilowatt installed in the United States. For a new geothermal power plant in field, operating and maintenance costs typically range from 1 to 3 cents per kilowatt hour. In power plant today, you would see about 5 cents per kilowatt hour charged to you as a consumer, and some plants will and can charge more during peak demand times. So over to the right here is a graphical representation of the market share for the geothermal energy market. It's dominated by 33% commercial market, followed by residential. 2 largest applications for geothermal energy production, and then industrial and other means are followed shortly after. Other considerations, you have key market drivers here. The rising concerns regarding environmental safety and increased demand for clean energy are the major driving factors for the geothermal market, and this is due to long-term sustainability, low maintenance costs, low environmental impact. Major participants, it's a global technology. North America, Europe, Asia Pacific, and Africa are all key players here. It's expected the Asia Pacific region will experience the largest amount of growth over the next decade. That's likely due just to that part of the world's rapid development. If you reference the project timeline down here below, you can see it's pretty extensive and has a pretty rigorous NEPA, the National Environmental Protection Act requirement, as far as drilling and implementing a geothermal plant, which is to be expected with any power plant implementation. You're looking at a 7 to 10 year project development time frame, and that's after you've already established your lease. So some of the key touch points here regarding your EAs go is environmental analysis go. You got to do your planning EA and pre-leasing EAs once you have your land available, and then you can start getting into your exploratory CX to be able to get your exploration activities lined out, the basic stuff, and then when it comes time to start drilling, you got to do a legitimate EA for your drilling stuff. And then you can start developing the well, and then push into the power plant and transmission environmental impact survey. Once all these are lined out, thumbs up from the EPA, NEPA analysis is complete, you can go ahead and move into constructing the power plant and getting that operational. So that just geothermal information resources largely reference, government energy websites for guidance on this. I'll be followed by Marcus for hydroelectric.
Marcus Hoversland, and I will be presenting on hydroelectric power. As you all know, hydroelectric power is just what it sounds like. Power coming from water, which is the hydro portion, and there are different setups that you can use for this. There are three main types, and basically they all, in one sense or another, use the potential energy of water stored at heights. It then flows through a turbine, connects to a transformer, and creates power. The three types are impoundment, diversion, and pump storage. So most common are impoundment and diversion, and I will get into those a little bit later, but pump storage is kind of something that's come up as of recently, and it's a little bit more unconventional. It has been around for many years. As you can see, the water mill in the picture was a form of hydroelectric power, but mostly it was used to power a grain mill to crush grain and create flour. A stat that I found on energy.gov was that there are 90,000 dams in the United States, and only 2,300 of them are being used for hydroelectric power. So impoundment, this is what you would think of when you get a reservoir of water and a dam that's holding that water. The water then flows through the dam as shown in the picture, and the potential energy of the water being stored above the dam is used with the kinetic energy as it flows down, and the turbine spins, which then generates power, goes through the transformer, and you can see that then that creates the electricity. These also have spillways that are used. And then the fish ladder so that fish can cross through the dam, and it's trying to be as minimal of damage to the environment as possible. The next form of hydroelectric power that we have is diversion. So in a way, this is very similar to impoundment. However, instead of building a dam and creating a reservoir, this form just diverts water from a river, and as it flows down the river, there is a diversion which pulls water off and kind of holds it in the forebay that you see at the left right here. The forebay then sends it through the penstock, which puts it through the powerhouse, which has, similar to the impoundment, has a turbine and a generator, and sends off the electricity through the transmission line. It returns the water downstream in the same river that we had seen up here. The third form is this pump storage that I briefly talked about. So this also uses the potential and kinetic energy of the water in the reservoir. However, during the day, the difference is this will use, say, windmills or solar power to create the electricity during the day, store that electricity, and then pump the water up to the upper reservoir during the night. Then, when daytime comes, the water flows from the upper reservoir down through the turbine, creates more power, which is shipped off to the grid, or potentially stored to run the same turbine. So these are a little bit different in the fact that you have to use energy to run the pumps and pump the water back up. And their capacity is based on gross capacity. So the amount that this produces subtracted from that would be the amount that is used to run the pumps. This is interesting because you don't have to be a part of a river or other water system. You just have to have some sort of gravity change. So that's where the height difference comes from, and be able to pump that back up to two different reservoirs. As you can see, water doesn't have to flow from the lower reservoir or into the upper reservoir so long as that's being created by precipitation. So a little bit about the geography of where this is. You can see that obviously with it being hydro, it's got to be around waterways, which typically come from mountains. So you can see a very dense amount of facilities along the Sierra Nevadas and the Cascade Mountains here on the East Coast. You can also see that the Rocky Mountains run through here. So I've included this map of the mountain ranges just as a reference to kind of tell where these mountain ranges run and how that water flowing down the mountain helps to run these power facilities. So then another set of them would be these Appalachian Mountains over here. That's going to have a very dense population, and it's pretty funny. I've never heard of the Boston Mountains, but you can see that they have a little bit more dense of hydroelectric power generation. So a little bit about the past capacity. You can see that the total capacity was growing quite rapidly, and then in about 1970, 1975 maybe it slowed down, and Nixon had created these bills that were a little bit more environmentally conscious and watching the waterways and fish and wildlife and stuff like that. And I believe that's what slowed down the growth of the industry, and we haven't really lost any capacity, but you can see that as some of those facilities get older, then there's maintenance costs and renovations and stuff like that. Though the capacity is very similar to what it used to be, that's still a little bit different. And so our population has grown. We've seen that our energy demand grows when that happens. And so with our capacity being the same, call it an average of about 280 billion kilowatt hours. I'd call that an average right there. And then the percentage of our total power consumption just keeps going down because our population's growing and our energy demand is growing. And so that's just kind of a little bit of the nature of the beast. However, there's still, you can see planned projects that are dealing with hydroelectric power. We have some that are, these green ones are approved. They have their preliminary permits, but then these yellow ones, they are pending preliminary permits. So you see there's a lot of green and yellow, and that's basically everything's in the permitting stage. There's only one that's under construction right there, and this is from the 2021 report, so that could be done by now. But you can tell these highlighted blue states are the ones that are using this for a renewable energy goal target. Lastly, I just wanted to kind of mention how the global stage plays out. There are 53 gigawatts that the United States and Canada have in the permitting phase, whereas you can see Eastern Asia is moving a little bit more. They have a percentage of theirs under construction, and that's 104 gigawatts. So a lot of the world are in permitting, but Eastern Asia seems to be moving a little bit more and getting to the construction aspect of it. And with that, just a couple of my resources that I used, and I hope that was informative for y'all. Shoot me an email if you have any questions.